Hey everyone, let's talk about Rolle's theorem. So this is a precursor to the mean value theorem. We don't usually use Rolle's theorem by itself very often, but we use it to prove something more general later. Mathematics is a step-by-step process. But let's see what this theorem is all about and how to quickly prove it using what we know. So what this theorem says, I don't know much about Rolle, other than that he proved this theorem, and I see his name in calculus books during this section. But what this theorem says is that, say you've got a closed interval, and say you've got a function defined on that closed interval, y equals f of x, and say you know a couple things. So you know that the function f is continuous. I use CTS for continuous on that closed interval. That means it's continuous at every single point in that closed interval. And say that you know that f is differentiable on the open interval, meaning that the function is differentiable at every single point inside that open interval, meaning that the derivative exists at every single point inside that open interval. Those are the things that you assume for Rolle's theorem. And then what you can, you need to assume one more thing. You need to assume that f of a equals f of b. And I've kind of got that sort of drawn here in the picture. And from that, you can conclude the following. You can say there must be some points in the domain strictly between a and b. It's not an endpoint, it's strictly between them, with the property that the derivative at that point is equal to 0. And actually, in the picture that I've drawn, you can see a couple of them. You could come down here at that local min. You could come up here. There's another one. So just because Rolle's theorem tells you that one such point exists doesn't preclude the possibility that the others could exist too. And you can actually prove this really fast using Fermat's theorem from a previous video, and using a bit of theory that we assumed but didn't prove. So first of all, what you can say is that given these conditions, first of all, given that it's continuous on the closed interval from a to b, we know that an absolute maximum and an absolute minimum does exist. That's true for any continuous function. And once you've got that, you can say, by our extreme value theorem, the maximum and or minimum must either be at an endpoint or at a critical point, not at the endpoint. And so there's two cases. So here's the first case. The max and the min are endpoints. And if that happens, then, well, one of them should be the max, one of them should be the min. Either way, because f of a and f of b are equal, that's telling you that the max must be equal to the min, which is telling you that your function y must be constant function, and so its derivative is 0 at every single point. So in fact, in this first case, the derivative at every single point is equal to 0, not just 1 or 2 or 3. And in the second case, that means in the second case, at least one of these points must be a critical point. So for Ma's theorem, or by this extreme value theorem, the max and min are either at endpoints or critical points. So it must mean there is a critical point. There is a point C with the max, say either the max or the min, and of course C is a critical point. Now if that happens, if you're a critical point, that means two things. Either your derivative is equal to 0, or your derivative doesn't exist. But we know that we are differentiable on the open interval from a to b. We've excluded the case where we're endpoints, so we're here at the open interval. We are differentiable, so it can't be true that the derivative doesn't exist. And so the derivative, being that it exists and you're at a max or a min, must be 0. So that's how you show Rolle's theorem. If you're continuous on the closed interval, if you're differentiable on the open interval, if you know those endpoints are equal, then there must be a point in the middle, at least one point, with a horizontal tangent line. And there's different ways that could happen. If your max and min are at the endpoints, then you're constant anyway. So at all the points in the middle, your derivative is equal to 0. Or if they don't both occur at the endpoints, the max or the min has to occur somewhere in the interior of the interval. And then you're in the situation using Fermat's theorem where it has to occur at a critical point. Your options are either the derivative doesn't exist or it's equal to 0, but we assumed that it does exist, so it does have to equal to 0. So then you get this really nice conclusion for Rolle's theorem. And in a later video, we'll use that to prove the mean value theorem.